Thank you for attending our seminar. And so first, the first 10 minutes, I will introduce a quick overview of our unit. Our unit is called the Succinct Information Processing Unit. And my name is Yasuo Tabe. I'm the unit leader of this unit. So research goal of this unit is develop algorithms and data structures for scalable knowledge discoveries. Recently, there is a large amount of data is generated, and we need to process those large data sets quickly. So that's why there is a large need for processing big data in various fields. We use succinct data structure as a key technology. It's a compressed data format supporting various operations of data structures. It does not need decompressed data. Application area includes string processing and chemoinformatics, graph mining, trajectory data analysis. Succinct data structures is a compressed data format supporting various operations. Usually, trees and graphs are implemented using pointer. The space is n log n bits. N is the number of nodes. And this log n term is too large for storing big trees. On the other hand, succinct data structure for trees represents a tree as an integer array, like this. The space is very small and order n bits of space. And we can, this succinct data structure for tree supports tree operations in constant time. And we need the compressed data and support various operations of this integer array representation of tree. Recently, many succinct data structure has been proposed for mimicking various data operations of data structures. Examples are strings, and trees, and graphs. So leveraging this succinct data structure, we would like to develop various data processing methods. Our unit was established in 2017, and we published 22 publication records and 3 press releases. And applications range from machine learning and string processing, chemoinformatics to trajectory data analysis. And those results are published in major international conferences like IJICAI, ICDM, Big Data, and ISMB and SIG spatials. So from this result, in this seminar, I will present several results. So from this slide, I will quickly present overview of our results. First result is a processing for highly repetitive strings. Highly repetitive strings is a string including many identical strings. This cartoon represents an example for highly repetitive strings. Substring ATGC appears 3 times in this string. So this string can be considered as highly repetitive strings. Real applications are genomes, genome processing, and version control documents like Wikipedia and source codes in repositories. Actually, in human genomes, 99% of genomes are identical. So these human genomes can be considered as highly repetitive strings. In fact, databases storing human genome have become large. In 1,000 human genome projects, database includes 1,000 human genomes. So we now would like to process these types of large genome data. So we developed the various string processing methods for processing highly repetitive strings. Like these are grammar compressions and LZ type compressors. Grammar compression is a context-free grammar in Chomsky normal form generating a single string. Grammar compression compress input string using grammars. Grammar compression is effective for highly repetitive strings because it can build a small grammar for strings including many substrings, many identical substrings. And grammar compression is an advantage. It has a nice representation as a binary tree like this. This grammar is equivalent to this grammar tree. And that's why we can design various string processing algorithms as a tree traversal on this grammar tree. And we developed a new dynamic self-index on grammar compression. It supports pattern matching substring extraction, insertion, deletion for a string. This result is published in DCC 2018. Recently, we developed a new compression algorithms for highly repetitive strings that is called LZRR, LZ77 parsing with right references. In this seminar, Nishimoto-san will talk about these algorithms. Second application is similarity search on integer sketches. Background is recently integer sketches have been presented for approximating various string measures. Sketch is mapping feature vector to integer vectors, and similarities between original feature vectors will be preserved for a pair of sketches as a Hamming distance. And the example for integer sketches is a consistent weighted sampling and a vivid mean hash. Actually, previous researches have focused on binary sketches so far, so there are no fast similarity search methods for integer sketches. And that's why we developed the fast similarity search method for integer sketches. Problem we would like to solve is to find all the sketches similar to a query from databases. And the result is we developed a new succinct try for space-efficient fast similarity searches. It at most 100 times faster than existing methods. In this seminar, Kanda-san will talk about dynamic version of similarity search method on integer sketches. Dynamic means the index allows dynamic operations such as insertions and deletions. And of course, it supports fast similarity searches. We also developed machine learning methods leveraging succinct data structures. We developed feature maps for string alignment kernels. Background is there is a large need for classifying large collection of strings like DNA and proteins. So existing machine learning methods, such as kernel methods, is not applicable to these types of large collection of strings. So existing method takes order cubed n time and squared n time memory for the number of n of strings. So this computational time and memory prohibit us to apply this machine learning methods to a large collection of strings. So we developed a new feature maps for string alignment kernels. Our results are our methods up to 2 order of magnitude less is best while keeping high classification accuracy. This result is presented in ICDM 2019. So in this seminar, I presented introduction of succinct information processing unit. Second speaker is Nishimoto-san, and he will talk about LZRR presented DCC 2019. And third speaker is Kanda-san. He will going to talk about dynamic similarity search on integer sketches that is presented in ICDM this year. The last year is Hide Pannai Sensei. He is a visiting researcher in Riken and a professor at Tokyo Medical and Dental University. And he is going to talk about the theoretical aspect of processing highly repetitive strings. This result is presented as Spire 2020 and got the Best Paper Award. So that's it for my introduction. And we move on to the second speaker. Please start. Nishimoto-san, please start.
Hello, I am Takaki Nishimoto, a postdoc working in Riken AIP. This is joint work with Yasuo Tabei. This paper was presented at Data Compression Conference last year. In this presentation, I talk about compression algorithms for highly repetitive text collections. A highly repetitive text collection is a set of very similar texts. For example, linear sequences and versioned documents. Many compression algorithms for highly repetitive text collections are proposed. For example, LZ77 random speedability and repair algorithm. And now we present a new compression algorithm named Ssrr by introducing the idea behind validation parsing into LZ77. LZ77 is the default standard compressor for highly repetitive text collections. So we first review LZ77 and validation parsing, and then present our Ssrr. First, I will explain LZ77. LZ77 greedy parses are given string into phrase in the left to right order. It selects the longest substring occurring left from the current position as a phrase. When such a substring does not exist, LZ77 selects a character as a source phrase. In this example, the first A and B are source phrase. The next phrase is ABABA, because ABABA is the longest phrase with left reference. The next phrase is AB, because AB is the longest phrase with left reference. The next phrase is ABB. So this is LZ77 phrases of this string. Next, I talk about the properties of LZ77. Each phrase can be encoded into the integers, and each character is recovered from a source phrase by following finite loop of references. For example, the red character A is recovered from the blue character A by following finite loop of references. So LZ77 achieves high compression ratio for highly repetitive text because the number of phrases can be small. Next, I will explain validation parsing. Bidirectional padding is pass a string into phrase with left and right references as the upper example. We call this phrase bidirectional phrase. The advantage of bidirectional padding is that the number of bidirectional phrases can be less than that of SS77 phrases. This is because bidirectional padding can use right references. However, bidirectional padding has some disadvantages. The first one is that infinite loop of references can occur by left and right references as the right figure. If infinite loop of references occur, we cannot recover the original string from bidirectional phrases. For this reason, bidirectional padding algorithm needs to pass the input string carefully such that the phrases have no infinite loop of references. The second one is computing smallest bidirectional phrases of a given string is NP complete. So practically, we use approximate bidirectional padding for data compression. Recently, some approximate bidirectional padding algorithms have been proposed. For example, LexPath and LCP-comp. Both algorithms choose phrase using the lexicographical order of suffixes of the input string and achieve high compression ratio for highly repeated text collections. However, the number of phrases is not always less than that of S77 phrases. Next, I will explain our Ssrr. Ssrr is a new bidirectional padding using the idea of SS77. Formally, Ssrr greedily passes a string into phrases in the left to right order using longest bidirectional phrases without infinite loop of references. In this example, the black rectangles are the phrases already created by Ssrr parsing. Considering the already created phrases, the next longest bidirectional phrases without infinite loop of reference is the red rectangle. So Ssrr chooses the red rectangle as the next phrase. Ssrr repeats this process until the input string is passed. We call these phrases Ssrr phrases. Ssrr phrases have not infinite loop of references because Ssrr padding does not choose phrases with infinite loop of references. Next, we introduce a phrase called LBP for finding the Ssrr phrases. ILBP is the longest bidirectional phrase referring to position I, allowing infinite loop of references. In this example, the black rectangles are the already created Ssrr phrases. Considering the already created Ssrr phrases, the third LBP is the blue rectangle. The string on the blue bar is the target string of the third LBP. The target string starts at position 3 because it is the target string of the third LBP. We can consider the LBP referring to each position. The LBPs have a property such that the longest prefix in the set of ILBPs without infinite loop of references is equal to the next Ssrr phrase. In this example, the red rectangle is the next Ssrr phrase, and its target string is a prefix of the target string of the third LBP. This is because the length of the Ssrr phrase is no more than that of the longest bidirectional phrase referring to the same position, allowing infinite loop of references. Next, I will explain the algorithm for finding the next SSRR phrase. The algorithm consists of 3 steps. As the first step, we compute the LBPs referring to each position in decreasing order of their length. At the second step, we compute the longest prefix of each LBP without infinite loop of references. By the property of LBPs, the LZR phrase is any one of the computed longest prefix. Else algorithm repeats the first and second steps until the next LZR phrase is found. This is the main process of SSRR algorithm. This main process needs to compute the longest prefix without infinite loop of references for a given ILBP. This task is the most important part of SSRR algorithm. Next, I will explain a naive method for computing the longest prefix without infinite loop of references for a given LBP. The naive computation is for loops of references on each character of the given LBP. The naive algorithm runs fast when the cycle of loop of references is short. However, it takes a long time in the worst case because loops of references can be very long. In the lower example, the input string is short, and there are only 4 bidirectional phrases. However, the loop of references on the last phrase are very long. So we cannot use the naive methods for fast computation. Next, I explain our idea for detecting infinite loop of references. We use the fact that an infinite loop of references occurs if and only if a character he refers to characters recovered from he. So we check if a given reference makes infinite loop of references by directly collecting each character he prime and the source character of he prime. For example, in the lower figure, the blue character A is recovered from the red A by finite of loops of references. So we directly connected the blue A and red A. We got this H direct reference. In this way, the reference from the red A to the blue A makes infinite loop of reference clearly. We manage direct references on the input string using disjoint sets R. Each set in R stores the position of a source character and positions of characters recovered from the source character. So the positions of two characters he and he prime are in the same set if a character he prime has a direct reference to a character he. Hence, we can store all the direct references on the input string using the disjoint sets R. Next, we store the disjoint sets by a well-known data structure called union-find data structure. The disjoint sets are frequently changed every time a new SSRR phrase is created. But we can quickly update the disjoint sets using the union-find data structure. Next, I will analyze SSRR algorithm. Here is the source code of our SSRR algorithm. For each SSRR phrase, the algorithm repeats 3 steps until the next phrase is found. The number of the repetition is k. K is the position of the next SSRR phrase in sorted LBPs. The total running time is order k alpha n. Alpha is the inverse Ackermann function, and n is the length of the input string. K equal order n in the worst case, but k is practically small. So the algorithm runs in linear time practically. The Ssrr algorithm uses a success array, inverse success array, LCP array, and union find data structure for Ssrr purging. So the working space is order n words totally, in total. Next, I explain the compression ratio of Ssrr. The number of Ssrr phrases is always less than that of S77 phrases. Formally, the following inequality holds. The right term is the number of S7 phrases of a string T. The left term is the number of Ssrr phrases of the reverse T. We know that the Ssrr phrases of the reverse T can recover the original T. We omit the proofs of the inequality. Next, I will explain our experimental results. We compared Ssrr with S77 and LexPath using benchmark datasets. We implemented S77 and LexPath in the standard manner using the success array for a given string. Our experiment uses 3 evaluation measures: the number of phrases, memory consumption, and execution time. Benchmark datasets are PISA and Corpus. This is well-known datasets for highly repeated text collections. Here is the result of the number of phrases. The smallest number of phrases for each file is depicted in bold. The number of Ssrr phrases is less than that of the other phrases in many files. And the number of Ssrr phrases is approximately 5% smaller than that of S77 phrases. Here is the results of execution times. S77 is faster than Ssrr, but the execution time of Ssrr is at most 4 times slower than that of S77. LexPath is the fastest, and the execution time of Ssrr is at most 6 times slower than that of LexPath. Here is the result of memory consumptions. S77 and LexPath use the same amount of memory. The memory usage of Ssrr is at most 2 times larger than that of S77. This is because Ssrr uses the union-find data structure, but S77 and LexPath don't use the data structure. Here is our conclusion. We present a new bidirectional purging named Ssrr. Ssrr always achieves a smaller number of phrases than S77 with a theoretically guarantee. In experimental results, the number of Ssrr phrases is approximately 5% smaller than that of S77 phrases. Our purging algorithm runs in order n squared alpha n time and order n working space. In experimental results, our execution time is at most 4 times slower than that of S77. The memory usage is at most 2 times larger than that of S77. The implementation of Ssrr is available at GitHub. Thank you.
Yeah, and if you have any questions and comment, please scroll to the bottom of the page and click the Q&A tab.
Yeah, so you can hear me. So I just have a question about, you said compression, but for compression, you actually want to compute how much bits it needs. So in your analysis, you compared how many factors you can compute with LZRR, and you have shown that in the experiments, number of factors is always less than what you get from LZ77. But if you look at how good you can compress, and it looks different, I think, because for LZ77, there are papers, for instance, from Paolo Ferragina and others about the bit optimal LZ77 parse, where they think about compressing the lengths. So and the references. So you want to have close references because then you can compress these small integers better. So I wonder whether you have studied also in this direction, that you actually really want to compress, not just counting the number of factors.
Encoding?
Yes.
This paper is does not consider
Yes.
encoding.
Yeah, but have you thought about? So
this paper is only text to phrases.
でもそのことに考えてましたか? Have you thought about that?
Encoding.
Would you like to use your slides or to answer the question?
What?
You don't need it. You don't need your slides?
No problem.
No problem. Okay.
I don't consider encoding for phrases in this presentation.
Okay.
I think that is necessary for
practicality, I think. So
that is a nice feature work. So
yeah,
we can collaborate.
It's collaboration is always welcome.
Yeah. Nishimo-san, have you tried encoding LZRR phrases?
It is interesting, but it is hard for me.
Okay. Yeah, thank you for your question.
You're welcome, and thanks again for questioning.
Hello everyone. My name is Shunsuke Kanda. Today, I'll talk about dynamic data structures for similarity search methods on integer sketches. The contents were also presented in this year's ICDM. Okay, these are the contents of this presentation. First, I'll talk about background and contribution. Let's start with introducing the similarity preserving hashing. It's a core technique for fast similarity searches, which randomly map vectors in a metric space, such as cosine or Jaccard, into sketches in the Hamming space. Sketches is so-called discrete strings. Basically, real-world vectors are high-dimensional, and computing the similarity measure is costly. But the similarity preserving hashing enables us to replace the vectors into sketches of low dimension, while approximately keeping the similarity. That is, many similarity search problems can be solved as the Hamming distance problem. So in this study, we focus on solutions for the Hamming distance problem. Here, we claim that there are two issues on modern similarity search. One is the generality. That is, traditional hashing algorithms produce binary sketches. Although modern hashing algorithms produce integer sketches like these, such as b-bit meanwise hashing and consistent weight sampling. But most similarity search methods are designed for binary sketches and inefficient for integer sketches. Another is the dynamics. That is, modern real-world datasets are dynamic and updated over time, such as web pages and time series data. But most such methods are limited to static datasets and or inefficient for dynamic datasets. To solve the issues, our challenge is to develop an efficient dynamic search method for both binary and integer sketches. I'll formulate the similarity search problem. Sketch X of length m is an m-dimensional vector of non-negative integers, like this. We have a dataset large X of n sketches from x1 to xn, which is a dynamic set of n sketches. Given sketch Y and Hamming radius R as a query, we want to quickly find similar sketches such that the Hamming distance to the sketch Y is within the radius R. Here, the Hamming distance is the number of errors in each dimension. For example, to the query, the Hamming distances for each sketch in the dataset are 1, 3, 3, and 1 from the top due to the number of errors like this. Then the first and fourth sketches are similar because the Hamming distance is normal than the radius R. In the problem statement, the two modern issues are contained. That is, the sketches are from integers, and the dataset is updatable. I'll shortly summarize state-of-the-art similarity search methods in dynamic problem settings. Most methods use hash tables for their data structures, but they have parameters determined by the dataset size and inefficient for dynamic datasets. Recently, Iqbal addressed this issue by using Ssrr, but it's not applicable to integer sketches. So in this study, we propose new methods, dynamic filter try, or DIFTS shortly, for dynamic datasets of integer sketches, which leverage try data structure instead of using hash tables and such trees. Okay, next, I'll talk about try-based similarity search as a preliminary. Try is an edge-labeled tree built by merging common prefixes of sketches from the root. The downgoing path from the root to a leaf represents the associated sketch. For example, the downgoing path represents the third sketch x3 in the dataset. The original sketch can be restored by concatenating the edge labels on the path. For example, the original sketch x3 032021 can be restored by concatenating the edge labels from the root 032021 on the path. The similarity search using try is performed by traversing try nodes while counting the number of errors to the query sketch like this. If the number of errors exceeds the query radius, that is R equal 1, we stop traversing down to the subtrees. In this figure, we can reach the leaf nodes associated with sketches x1 and x7. That is, x1 and x7 are similar. The search is fast for small Hamming radius, and the time complexity does not depend on the dataset size. Here, the size is n. If the radius r is large, the similarity search becomes very slow because the time complexity is exponential to radius r. But we can relax the time complexity by using the multi-index technique, which I will not present here. But anyway, the try search can perform well for any radius in practice. I'll mention two issues on try implementation for similarity searches. One is scalability. That is, try for large database maintains many pointers and consumes huge memory. Then, reducing redundant nodes is an often used solution. But there is no reduction technique for similarity searches. This is because try has been traditionally used for text processing. The other is generality. That is, sketches consist of integers from the universe of size sigma. Here, sigma is a given parameter depending on hashing techniques. For example, sigma no more than 4 is recommended in meanwhile hashing technique. On the other hand, sigma no less than 16 is recommended in consistent-based sampling. But existing try implementations have been designed for byte sketches. That is, sigma equal 256. This is also because try is very used for text processing. As presented from the next slide, our new method Dift is a new similarity search method to solve the issues. I'll talk about our method dynamic filter try or Dift. First, I'll present the node reduction technique for the first issue about the scalability. I'll present the data structure and algorithm of Dift. It's a try-based similarity search method for binary and integer sketches. The basic idea is to store only some of try nodes around the root, like this, for memory efficiency, and exploit the try search algorithm for filtering out dissimilar sketches. That is, we perform the search algorithm on the compacted try and obtain candidate solutions, including false positives. Finally, we verified the candidate solutions by exactly computing the Hamming distances and remove false positives. In this example, x4 is a false positive because the Hamming distance is more than the radius. x1 and x7 are similar because the Hamming distance is less than, no more than radius. The update procedure is also very simple. Given a new sketch, we visit the deepest reachable leaf node V using the given sketch. And we append it to the posting list LV. After the appending, if the length of the posting list exceeds a threshold tau, we split the posting list and create new leaf nodes to make short posting lists. In this figure, leaf node V is split into two new leaf nodes. As I presented, the data structure and algorithm are very simple. But there is a crucial problem for the splitting threshold. That is, what is reasonable value of the splitting threshold? If the value is large, the posting lists become long, involving large verification time. On the other hand, if the value is small, many trials are created, involving large traversal time. The right chart shows actual search time results using 3 thresholds, tau equal 1, 10, or 100, varying the dataset size n. As you can see, the best thresholds are reversed as the data size increases, and the gap can be 1 order of magnitude and is very large. A reasonable threshold can be determined depending on the configuration of the dataset and given parameters of hashing techniques. If the dataset is static, we can search such a reasonable value using a grid search. But it's impossible for dynamic datasets, unfortunately. To address this problem, we propose an optimal threshold, tau star. To define it, we first construct a search cost model. Then we determine optimal threshold, minimizing the search cost. That is, the optimal threshold offers a case that can maintain the smaller cost from 2 cases of keeping or splitting the posting list after update. The right chart shows the search time results, including the optimal threshold one. As the blue line shows, the optimal threshold can always achieve fastest similarity search by maintaining reasonable posting list lengths. I'll present the definition of the search cost to determine the optimal threshold. But the formulation is somewhat complex, so I'll conceptually introduce this. The search cost is given for every node V in Dift. And the search cost for node V is defined by the reach probability and computational cost. The reach probability, denoted by RP, is the probability of reaching node V from the root using a random sketch from a uniform distribution. The computational cost, denoted by CC, is the time cost of the computation for node V in the traversal, which is defined for inner and leaf nodes separately. For inner node V, the computational cost is for checking the children. For leaf node V, the computational cost is for verifying the associated sketches. That is, we have 2 types of search costs for inner and leaf nodes. By using the search costs for inner and leaf nodes, we can derive the optimal threshold. Again, the optimal threshold offers a case that can maintain the smaller cost after update. Then, we compare the search costs in the 2 cases if keeping or splitting a given leaf. If keeping leaf V, then the search cost is maintained. If splitting leaf V, then the search cost is updated as the formula. By comparing the 2 search costs, we can derive the condition if the right case can maintain a smaller search cost. That is, it's the optimal threshold. By assuming a uniform distribution, the optimal threshold is related only to Hamming radius R and sketch length L and integer size sigma. So the optimal thresholds can be pre-computed, and the computation of optimal thresholds does not become a runtime bottleneck. By using the optimal thresholds, our Dift can grow the data structure while maintaining fast similarity searches with few node pointers. Okay. Next, I'll present the node implementation technique for the second issue about generality. But the implementation technique is very technical topic, so I'll briefly present this. To implement Dift, we have many try implementations because try is well-used data structure for text processing. But unfortunately, they are designed for byte strings and unsuited for integer sketches. Thus, our approach is first reconstructing integer sketches into byte ones, and then representing them using the adaptive radix tree, which is a space-efficient try implementation. By the approach, we can leverage an existing try implementation for similarity searches on Dift. I'll shortly present the data structure of the adaptive radix tree. The adaptive radix tree adaptively selects a space-efficient node implementation depending on the number of children. We have three types of node implementations. For a node with few children, we use a list-based data structure. For a node with moderate children, we use a hybrid data structure of a list and an array. For a node with many children, we use an array-based data structure. Each implementation has a different memory usage related to the number of children. So we select the most memory efficient one depending on the number of children. But the adaptive radix tree is not designed for similarity search, so we slightly modified it for node traversal in similarity search. Okay, before providing experimental results, I'll once summarize the contents until this slide. First, we claimed there is an issue on modern similarity search. That is, there is no efficient dynamic data structures for integer sketches. For this, we developed Dift based on try data structure. Then we claimed there are two issues on try-based similarity search in practice. For the scalability issue, we constructed a search cost model and defined an optimal threshold and reduced Dift nodes while maintaining fast similarity searches. For the generality issue, we reconstructed integer sketches into byte sketches to leverage an existing try implementation techniques. Okay, finally, I'll show experimental results for the performance of our Dift. I'll show results using 260 million compound protein pairs, where each pair is represented as a 3.6 million dimensional binary fingerprint. We converted the fingerprint into binary and integer sketches using Lee's min-hash algorithm for Jaccard similarity. And we constructed an index by inserting sketches in random order. And we produced the query set by randomly sampling 1,000 sketches from the dataset. we implemented all data structures using C++ of version 17, and the source code is available at our GitHub repository. First, I'll show the experimental results for optimal threshold. The figures show the average search times varying the dataset size N for binary and integer sketches using different Hamming radii 2 or 4. The blue line shows the results for optimal threshold, and other lines show results of fixed threshold. As you can see, the optimal threshold provides the fastest similarity searches in most cases. On the other hand, the search times with fixed thresholds are reversed according to the dataset size. The result demonstrates that our optimal threshold is effective for dynamic datasets. Next, I'll show the comparison result to state of the art. I'll first show the results for binary sketches. The figures show the average search time, update time, and memory usage varying the dataset size N. Our diact is depicted by blue line. For binary sketches, our diact is 4 orders of magnitude faster than the state of the art on the search time. And the update time is competitive, and the memory usage is at most 13 times smaller. The result demonstrates that our diact is an efficient similarity search method for binary sketches. Next, I'll show the results for integer sketches. As the blue line shows, our diact is always faster than state of the art on the search time, and the update time is competitive, and the memory usage is always smaller. The result demonstrates that our diact is an efficient similarity search method also for integer sketches. Okay, as I presented, we developed an efficient dynamic similarity search method for binary and integer sketches. The performance outperformed that of state of the art. Okay, thank you for your attention. Any question?
Again, so thanks for unmuting. So I have a question about the data.
Please speak clearly and slowly.
Okay, so can you hear me now? Is it clearly and slowly?
Yeah.
Okay, good. So my question is about the input data.
Yeah.
If you have the input data and I think you applied the min hash, then actually what you get is kind of roughly something, but it's not really precisely. I mean, the integer sketches, I think you can allow in the Hamming distance all the errors. So it does not have to be exact, I think, in your setting. Or say kind of exact, and you want really to have the exact difference in the Hamming distances.
That is the gap of the Hamming distance between the similarity measure.
Yes.
Yeah, it's a nice question, but sorry, in this study we did not consider the gap of similarity because the gap can be controlled by the Hamming distance by setting the Hamming distance threshold and whether the users need to reduce false negatives, or the users can allow some false negatives. The reasonable Hamming distance can be varied.
Okay.
So it is difficult to set reasonable Hamming distance threshold.
Okay, I see.
Completely. So in our experiments, we set well used Hamming distance threshold. That is almost 20% for the sketch length. Yeah.
I see.
Yeah. Yes, but for depending on applications, as you said, we need to investigate a reasonable threshold and the applicable data structure.
Right. Yes. Thanks. I mean, this. Can I ask another question? Again, about if you don't, so the Hamming distance, if you have, for instance, integer 3 and 4, then they're not equal, so you count 1. If it's 1 and 4, then it's also not equal, so you count 1. But maybe you have a data where you want to have just a difference. For 3 and 4, they're close, so you just have a penalty of 1. But if it's 1 and 4, then it's a distance of 3, so you have a penalty of 3, so you have 3 times more. So I think, can you use your data structure also in this setting where you don't use the Hamming distance, but the distances between each integer of your integer sketch?
Sorry, I can't hear you. That is.
So you use the distance between each integer of each of a sketch. Can you also compute in this setting what you did with the Hamming distance?
That is the computation approach for Hamming distance on integer sketches.
Yes. So my question is, what if you can exchange the Hamming distance with another distance?
Okay. I see. Thank you. For example, edit distance, a simple similarity measure like edit distance for strings can be replaced, but cannot be directly replaced.
Okay.
Because our optimal threshold is designed for Hamming distance, and the crucial property is the sketch length is the same.
Okay.
But for edit distance, the sketch length, the string length is often different.
Yes.
Then our design will be different. But the program setting is also important and interesting.
Okay. Thanks.
Thank you.
Okay, I will start. Okay, so I will talk about repetitiveness measures on 2 Morse words. This is work presented at Spire 2020. This is a joint work with my colleagues in Kyushu University. And so the subject is sort of related to what Nishimoto-san talked about, but it is much more theoretical in nature. I don't have any algorithms, but this is just sort of an analysis of how compressible some repetitive measures, analysis of repetitive measures on a family of strings called 2 Morse words. So the big problem behind this motivation is when you're given a string, you want to know how compressible is this string. And so you might think the ultimate compression is, of course, Kolmogorov complexity, but unfortunately, it's incomputable, so it's difficult to know the exact value. Another well-known measure is empirical entropy, which basically is based on the average number of bits needed to represent each symbol of the string. But it's known that it's not very good at representing the repetitiveness of what are called highly repetitive strings. This is what Tabe sensei described earlier. So for example, multiple genomes of the same species are very similar. And if you have a set of them, even if each one of them aren't compressible, the set as a whole is very compressible. But this, using this entropy measure, it doesn't capture this repetitiveness very well. And so for highly repetitive data sets, the dictionary compression schemes have been known to be effective, and this has been catching attention. It's a hot topic in the string algorithms community. And so, there are many dictionary compression algorithms and representation schemes. The algorithm presented by Nishimoto-san earlier is a type of dictionary compression. And so there are many measures based on specific algorithms or some form of representation which fall into this category. Here are just a few. You don't have to remember all of them. I will just use the Z later. This was introduced earlier also by Nishimoto-san. So these are sort of ad hoc measures, and to unify and generalize these measures, recently Kemba and Pretza proposed a concept called string attractors, and I will denote this by gamma. And it is known that the measure gamma for a string W is a lower bound for all these dictionary compression measures. And yet another measure more recently proposed is a measure called delta. I don't know if there's another name for it. I only call it delta, so I don't have a good name like string attractor. They don't give a good name like string attractor, so it's a long description. But it gives a lower bound. It lower bounds actually gamma, so it's smaller than gamma, and so it's smaller than all of these dictionary compression schemes. So these measures are not, by definition, compressed representations, but these capture the repetitiveness of the string. And these are interesting because for any strings, you can build, it is known that you can build text indices of size that are almost gamma or delta with a log factor. And so you can do efficient search on this string with a compressed size. And for delta, the Koshumaka et al. Showed that this is sort of optimal in the sense that strings and some string families require this much space to even just representing it. So, so it seems that delta is a better measure than gamma, but we're not completely sure because the analog for this is not known for gamma, and we don't know yet if we can represent any string W in the gamma space. So our work is sort of goes in this direction. It doesn't solve it completely, but so what we want to do is we want to study characteristics of specific values of gamma for specific strings. So this was actually started by, maybe not started, but it was recently studied by Antazia et al. And they studied the values of gamma for several well-known families of strings. So they showed that for standard Sturmian words, I won't define it, but so these are Fibonacci words are examples of these words, and they showed that the gamma for a standard Sturmian word is constant for any standard Sturmian. And also for the nth Morse word, which I'll define later, I will denote it by Tn. And they showed that for any two-most word n two-most word Tn, that gamma is less than n. So they showed a string attractor. So I will yes. So I will define what a string attractor is later, but they showed that gamma is upper bounded by n, and they conjectured that this was optimal. So in this work, we continue this line of work and study gamma and also delta for the two-most words. So our result is as follows. We first showed that the gamma is actually not n, but actually a constant 4 for any n greater than or equal to 4. And so we disproved their conjecture. We also show that delta, the exact value of delta, which is this, and we also show the exact value for z, the LZ77 factorization, which is n is 2n. So yes, so I will define all these concepts as they appear. This is just an overview of how the proof proceeds. We first show that gamma is upper bounded by 4, and then we use this result because delta is always at most gamma. It gives a lower bound. We use it to prove a lower bound of 4 for Tn, and so we get this result. So now I will start defining what these concepts are. So string attractors is the definition of string attractor is this. So a set gamma of positions of a string W is a string attractor of W if any substring X of W has an occurrence that overlaps with some position that is in the set. So and we will denote the size of the smallest string attractor of W by gamma. So for example, for this string, there always exists a string attractor because if you choose all the positions, any substring will overlap with some position in the set. And actually, 3, 5, 6 is one of the smallest string attractors of W, like this. And any substring that overlaps with 3, 5, or 6 is okay. And you only need to check if A, B have an occurrence that overlaps with 3, 5, 6, and AB has an occurrence here, and also an A has an occurrence here. So any substring of W has an overlap with positions 3, 5, and 6. And you can check all other combinations, and you can see that any combination of 2 positions won't give you a string attractor. So gamma W is 3. And next, what are two-most words? So it's defined like this, but so it's very easy. I think it's easier to see examples. The T0 is A, T1 is AB, T2 is ABBA, and so on. And in order to define it recursively, we define also S, which is obtained by flipping the A to B and B to A of T. So T1 is AB, then S1 is BA, T2 is ABBA, then S2 is BAAB, and so on. So this is a two-most words, and each the nth two-most word has length 2 to the n. Okay, and so what we want to do is we want to know the value of gamma for each of these strings. And so first we will prove this statement. The upper bound for gamma, and so the claim is that this set of 4 positions is a string attractor for Tn. So before going into the proof, I will first represent the two-most words as a tree, a perfect binary tree, like this. So the root is the nth two-most word, and because it is recursively defined as Tn-1 and Sn-1, we can make a tree out of the two-most word. And so the leaves correspond to characters at each position of the nth two-most word. And I will call the center of an internal node the rightmost position of its left half. So for example, the center of the root is here because it's the rightmost position of the left half. And for this node, the center is this position, and so on. Okay, so here's the proof. So first, I will consider the length 1 substring, which consists of A or B. So first, and so these 4 positions are the positions I said are the string attractor for Tn. And if you consider this position and this position, they are the last characters of Tn minus 2 and Sn minus 2. And so because Tn minus 2 and Sn minus 2, they flip A and B, we know that these have different characters. One is A and one is B. So we know that at least A occurs here or here, and B has an occurrence here or here. So for length 1 substrings, we have an occurrence that overlaps with the position in the set. And so it remains to show that any substring of the 2 most words of length at least 2 has an occurrence that contains one of the 4 positions. Okay. So I will prove this in 2 steps. The first is I claim that any node in the tree has an occurrence such that its center coincides with one of the 4 positions. Okay, so for the node, these 4 nodes, it is very straightforward. So for example, the root Tn, the center is this position, so it coincides with one of the positions in the set. For Tn minus 1, this occurrence, the center is here, so it coincides with this position. And for Sn minus 1, the occurrence here, the center is here, so it coincides with this position. And for Sn minus 2, this occurrence, the center is here, so it coincides with this position. Okay, and what about for other nodes that are lower in the tree? So actually we can say that for any node Tk or Zwickau Sk, it contains an occurrence of Tk minus 2 with the same center. What this means is, for example, for Tn minus 2, if you look at the tree long enough, you can see that there's an occurrence of Tn minus 2 right here, because by definition, Tn minus 2 is the concatenation of Tn minus 3 and n minus 3. So the center of Tn minus 2 is here, and it coincides with this position, and it is also a center of Tn. So the center of Tn matches the position. So there is an occurrence of Tn minus 2 that matches the position of the center of Tn. Okay. And for even smaller strings, for example, Tn minus 3, you can find an occurrence here, and this gives this is the center matches the center of Tn minus 1, and for Sn minus 3, you can find an occurrence here, and this also the center matches this center and overlaps this position. It coincides with this position. Okay, and so on. You can always go down all the way down to the tree. So I've proved this claim. So with this claim, now I will consider any substring ij, Tn, ij of Tn of length at least 2. And now consider the lowest common ancestor of the leaves that are at position I and j. So there's a leaf ij here, and we take the lowest common ancestor. So that means we go up the tree until the 2 paths merge. So this is the LCA of I and j. And from the previous claim, we know that this LCA will have an occurrence such that its center coincides with one of the 4 positions in the set. And also, because it is an LCA of I and j, we know that Tnij is a substring of the LCA, and it overlaps with the center of LCAij, which is this position. And because what we said before, this means that because this has a position whose center coincides with one of the positions in the set, this substring will have an occurrence that overlaps one of the 4 positions. So that proves that these 4 positions is a string attractor for Tn. So that gives us a lower bound, an upper bound, and now for the lower bound. So to prove the lower bound, we use the second result, which is the exact value of delta. I haven't defined delta yet, but the only characteristic we'll use here is that the exact value is this, and it lower bounds gamma. And if we use this result, we know that for any n that is at least 6, if you plug in 6 in this formula, you get 3 point something. Okay, so it's larger than 3, and because it's monotonically increasing, and also it lower bounds gamma, we have this formula, and because gamma has to be, by definition, an integer, we know that gamma has to be at least 4 for n greater than or equal to 6. And for smaller values of n, we just prove it by exhaustive search, and we can find these values for. And so that gives us this, and because we also have a matching upper bound, we know that the gamma is 4 for any n greater than or equal to 4. Okay, so that is the result for gamma. And now, what is delta that we used in the earlier proof? So delta is defined as follows. So let dkw be the number of distinct length k substrings in W. And then delta is defined as the maximum of dkw over k for all possible k. So for example, this string of length 6, so we have k from 1 to 6, and for each length, we consider all the distinct substrings. For length 1, we have AB. For length 2, we have 4 substrings, and so on. And so the number of substrings is here, and this is just doing division. And the maximum value here is 2, so delta for this string is 2. And so how do we get the value for delta for 2 Morse words? Actually, it relies heavily on previous result by Brolek. He characterized the exact value of dk/tn for as this formula. So what we need is k over dk/tn over k. And so because this is an explicit formula, we can just maximize, use this result to maximize this value. And doing a little math, you get that the maximum is actually this formula. Yeah, so it's not very hard. And finally, I said we compute the exact value of the LZ77 factorization. So the definition of LZ77 factorization is the same as what Nishimoto-san described. This is just an example. So it basically is a greedy parse, and you take the longest. So for each factor, you take the longest prefix of the rest of the string that has a previous occurrence. So, or if it doesn't have a previous occurrence, just one letter is the factor. So the first factor is A, the second factor is B, and the third factor is A. The fourth factor, so AB appears previously and so on, but ABB doesn't occur previously. So we parse up to here and so on. So the size ZW for this string W is 5. And we prove that Z for 2 Morse words is 2n. And this is done by induction on n. So T1 is AB, so we get 2 for Z. And we use induction on the for the upper bound and also the lower bound. For the upper bound, we assume that the formula holds for any k less than n. And then what about for Tn? So because Tn minus 1, we know the value for z for Tn minus 1 is at most 2n minus 1. And this substring occurs here, and this substring occurs previously. We can see that z of Tn is upper bounded by z of Tn minus 1 plus 2, because you can have only at most two phrases when you add Sn minus 1 to Tn minus 1. Okay? So we get that Ztn is upper bounded by 2n. And for the lower bound, we do a similar thing. So we assume that Ztk is lower bounded by 2k for any k less than n. And so we use another result by Berlek again that says that any substring that is longer than 2 to the n minus 2 in Tn is unique, meaning that it occurs only once. So if we consider these two positions, the substring from here to here has length 2 to the n minus 2 plus 1. So this has to be unique, which means that it doesn't have a previous occurrence, which means that it can't be in the same LZ77 factor. So there has to be some factor boundary between here and here, and the same can be said for these two positions. So there has to be at least two new factors when we add these two new blocks to get Tn. Okay, so this says that Ztn is lower bounded by Ztn minus 1 plus 2, and thus from the assumption we get it's lower bounded by 2. Okay. And the above two upper and lower bounds give us that Ztn is 2. So here's the summary of the results. So the blue lines are what we showed, and the bidirectional parse or bidirectional scheme, the smallest value is not known yet, but we conjecture it is n plus 2. And if this holds, the two Morse words could be the first example that shows a gap between gamma and B, which implies a gap between gamma and dictionary compression schemes. And it might, and so we might be able to say that delta is a better measure for than gamma. Okay, that's it. Thank you. Any questions?
Okay. Thank you for your talk. And any question and comments?
So actually, I shouldn't ask because he is just right next door. Perhaps you could again, for the last slide where you said that you don't want to have that, or you expect that gamma is not good measurement for the compressibility. I kind of in doubt because in this example, gamma and delta are constant. So if you show, or if somebody shows that the bidirectional scheme has a linear number of phrases that actually does not put gamma in a bad light, I think. It only
yes, so the problem is that gamma is NP hard to compute, yes, and delta is always smaller than gamma.
Yes.
So if you can have an index of size delta log n, it should be better than gamma log n if there is a gap.
Okay.
I think.
Yeah.
But yeah, I'm not sure, but yeah, I think that means.
If you know how the index on gamma will look like, or
because there's always the constant factor I don't know about, so
yeah. Good.
It may not be true, but yeah.
Thanks for clarification.
I think there are no questions, so thank you for your talk. I have final remarks. So
I think you should show your face.
Can I use my slides? AIP Open Seminar is also held in the next week. So the team is Imperfection Information Learning teams. Please join if you have an interest. So thank you for attending this seminar, and hope to see you again.